Hello. Oh, good evening. Are you able to hear me? Hello.
Yes, sir.
Great. So actually today is not revision session. So this is week 6 only, but two pending concepts are there in the week 5. Hope you know that. I think two algorithm concepts of minimum cost spanning tree. First we'll finish that part of the week 5. Then we'll move to the week 6. Maybe we may not finish at the week 6 completely because week 6 has again a set of concepts are there and algorithms are to be discussed. But anyway, upcoming quiz one, we have a mock. Today it is released, the mock quiz one. Day after tomorrow session, we purely discuss on that 1 to 4 weeks concepts overview and as well as the mock quiz questions. That is on Friday session. So that is what our plan in this week. So Disha, you want to ask something?
No, sir. I'm just wanted to know when is the mock release.
Yeah, mock release is released today. I hope you are able to access it. Am I right? Hello. Can you please check your dashboard? I think it was released.
Okay, sir. One.
Okay, you please check it. Huh? So let me
Sir,
share.
when is the revision session?
That's on Friday. Friday.
Okay.
So is my screen visible? Okay. Yeah.
Yes, sir. It's
So
released.
look at it. So so this is a pending concept. Actually, first let us finish up that. Some pending concepts of week 5. Two algorithms and two concepts are pending. That is spanning trees. So this concept is pending, which is actually takes very little time. Maybe algorithms is somewhat it's there, but easily you can understand. So hope my writing is visible. What I'm writing, spanning trees have written. Is it visible? Okay, okay, great,
Yes, sir.
fine. So look at that. A graph which has that maybe a cyclic graph is there. Maybe if you could look at this same kind of graph in the GitHub notes, what is that? Same thing I extracted. It is a cyclic graph. You can say that you started from zero and you keep going one, two, three. Again from three, you can come back to the zero. So a graph might be a cyclic one, but the tree is not a cyclic one. Simply, you can say that spanning trees it is a cyclic graph. Make sure it is a cyclic graph. We don't have any cycle. Like where you started, you don't have that another reverse edge or another edge from again you are reaching. But it is definitely a derived from the graph. So spanning tree is definitely derived one. So what exactly the spanning tree is? We are selecting, you know, all possible edges where you can get it. All possible edges, all possible edges without forming that cycle. All possible edges or paths which doesn't form that cycle. And weights sum, whatever that weight sum you are doing, that's going to be that optimal or minimum. What you can say that minimum. That's the reason what we call as minimum cost spanning tree. Minimum cost spanning trees. So in short form, they call it as MST, minimum cost spanning trees. First, let us understand what really the spanning tree. As I said, from the graph, we are making a sub-derived tree that's called spanning trees. Let's have that example of spanning tree. Example of spanning tree. So, for example, you might have one particular graph like this. Maybe I don't want to name this particular vertices, but it is having that four vertices and four edges are there. How many spanning trees are possible is, so maybe st1. So it looks like this. Maybe this, this. Is it forming cycle? Definitely not. You might have another spanning tree. Maybe ST2. ST2 is like this. Is it right? Another spanning tree is like this. You might have another spanning tree. So something like this. Multiple spanning trees. See, now you got it already three spanning trees. Like top open, and then we have another one. You can have that spanning tree. Three is over. You might have another spanning tree. Four. Maybe bottom edge is not there, where it is not creating a cycle. Definitely it is a cyclic graph. So multiple spanning trees are possible, but you might have some weights, maybe associated with some weights, because already this week 5 is completely talks about that. A graph with edge weights are there. So minimum cost spanning tree, what it will choose is, it chooses minimum total cost of that. So out of these four spanning trees, whichever the total cost is less, maybe this is a cost 1, cost 2, cost 3. Maybe this is a cost 2, maybe cost 3, this is cost 0. Maybe this is a cost 1, this is cost 0, here it is cost 3. So maybe you are having it as a cost 1, so you are having cost 2, cost 3 is avoided, so cost 0 is. See, one of the cost is missing. So did you understand that? So out of these four spanning trees, we choose minimum total cost. Total cost. So total cost of edge weights. So total cost of edge weights means maybe C1, C2, C3 total, or C0, C2, C3, or C1, C0, C2, or C1, C0, C3. So hope you got it. What is spanning tree? Is it clear? Is it clear? Just you raise your hand. That's like thumbs up or something. That makes you understand. Yeah. So great. So now to generate that MSTs, so there are two different algorithms are there. The first algorithm is the Prim's, and next one is critical. Approaches are different, but both will generate that same kind of graph. So whenever that graph you have taken the same graph, you applied that Prim's algorithm, you applied the critical algorithm, the outcome is same. Even you are applying Prim's, even you are applying critical algorithm, the next algorithm, the outcome is same. First, let us work with the Prim's. So how really the Prim's it works? So the Prim's is very simple. So what we do is, we choose one vertex as I'm working with now Prim's algorithm. So what we do is, the first step is that choose any vertex as origin. So whatever your starting vertex which you want to choose it. For example, if you consider this is the graph, maybe you choose it. This is going to the starting point of it. Maybe starting vertex. So after that, whatever you do that this particular vertex, maybe you have chosen that the vertex number 0. This 0 is having the two adjacents, like you have an edge from 0 to 1 with edge weight of 10 is there. 0 to 3, there is edge weight of 80. Out of these two, we are choosing the minimum one. What is the minimum? What is the minimum? What is the minimum? Hello.
10, sir.
Yeah, 0 to 1 edge is minimum, because once you chosen that starting vertex is 0, then we choose a minimum adjacent edge from 0. So actually we have two choices. The first choice is that 0 to 1, there is a edge weight of 10 is there, or you can choose 0 to 3, there is a edge weight of 80. So we clearly opt for the first one, because This 10 is the minimum, comparatively this 18. So that this particular edge, what we do is we are trying to add it into my into sorry, I'll change my again black color. So then what I'll do is I will add this one into that. There might be a dictionary called, total edges, where I'll update it. It might be a list. It will update with 0 and 1. Maybe, 0 to 1 edge is going to be added, because out of these two, the minimum one is the 0 to 1 edge. So we have done this. Then from this particular one, again you are choosing the minimum. So whenever whatever the remaining edges are there comparatively, so 0 to 3 there is a edge is there, and then we are having some more edges, like this 18 is pending. Maybe I'll make it choosing this 18 is pending. From the one, there is a edge called 6 is there, that is 1 to 3 is there. There is a edge called that 1 to 2 is there. Out of these three, which one is the minimum? Which one is the minimum?
1, 2, 3.
Yes. So now in the next step, whatever the next step, what we do is, in the next step, next we choose again the minimum of three edges. Already three edges are available. The first edge is available as 0 to 3, 18 is there, and then we are having that 1 to 3, there is a 6 way it is available, and one more is available, that is I think 1 to 2 is 20. Yes, so 1 to 2 20 is there. So we are choosing it as 1 to 2 20. So out of these three, what is the minimum is, we opt for that 1 to 2. So immediately what happens is, whatever my particular total edges is there, that is updated with one more edge, that is updated value of my t is, so it's going to be updated with 0 to 1 edge is added, and 1 to 3 edge is added. So next one, so once this is done, so already my particular edge it is selected as, I'm making a green color here. This is selected, this is selected, so that these two edges are selected. So now we are going that. So next time we are having availability of 0 to 3 or 3 to 0 is available, and then 1 to 2 is available. Am I right? Then next minimum two edges are there, no? Is it there? From 1 to 2 is available, and 3 to 0 also available, or 0 to 3 also available. But whenever you are choosing a edge, it tries to select that whether the cycle is formed or not, because basically the property of that spanning tree is it should not form a cycle. So the available edges are these two, like 0 to 3 18 is available, 1 to 2 20 is available. So is there any possible way to connect that 1 to 2 other than this 20? No possibility. Is it there? Is it there? Is it there or not? Hello?
No, sir.
So no possibility. But we cannot choose that 3 to 0. The reason is, so we don't choose next minimum 0 to 3 or 3 to 0, because forming a cycle. It should not form a cycle. So forming a cycle. So we don't choose it. Cycle. So it's forming a cycle, so that we don't choose this one. We don't choose this one. We don't choose this one. So when you don't choose that one, again we have only one alternative to connect this two immediately from the one, that is, so 1 to 2. So that the next adjacent we are selecting is 0 to 1 is over, 1 to 3 is over. So now we are going to select that 1 to 3. So this is done. So now, so that we got that another edge, that's green color. So we got this edge, we got this edge. We don't select 3 to 0 or 0 to 3, but we are selecting this. Okay, that's what we have done. So next, from to connect this 4, we have two ways. 3 to 4 is available, 2 to 4 is available. Which one is the minimum? Which one is the
2 to
minimum?
4.
So that 2 to 4. So that we got it. So the final, the particular MST minimum cost spanning tree, it looks like this one. That is 0 to 1, and then from the 2, sorry, 1 to 2 is there, 1 to 3 is available. So 1 to 2. So from this 2, 4 is available. So this is weight of 10, this is weight of 6, this is weight of 20, and this is weight of that 8. So total it's going to be 10, 16, and then 36, 36, and this is going to be that. Total cost is that this MST cost, total cost is that optimized cost, MST or MCST or MST, total cost is 40. This is what the PRIMS algorithm. Please see this, the coding approach. So maybe you should understand what really that particular description in this notes has been given. Remember, retain a minimal set of edges, because n number of vertices are there, means definitely we are connecting all of them with n minus 1 edges only. That's called so minimum number of edges we are using. And the second one, you can see that, recall that minimally connected graph is a tree. As I said, it doesn't form a cycle, it's a cyclic one. That makes sure that. So adding an edge to the tree creates a loop. So for example, if you are simply add one edge to the particular MST, it creates a loop. See, look at here. Already your particular MST is created, the green color one. If any edge, if you add it, immediately it creates cycle. Maybe you'll add it, so edge is from here, it creates cycle. So maybe you'll add it, edge is here, it creates a cycle. So that it is simply a tree. Simply if you add a one particular edge, it creates a loop, it creates a cycle. Removing an edge to that particular MST, it disconnects a graph. For example, any particular edge, if you remove it, for example, I remove this, then what happens, this 0 will become as a separate component. This 1, 2, 3, 4 will become as a separate component. So it becomes like, disconnected graph, what you can say is. So the next one is, so want a tree that connects to the all vertices. So all vertices you are connecting is called as a spanning tree. Just it is simply connected tree, what you can say is. And the next one is that, as I said earlier, more than one spanning tree is possible. So for example, equal length of weights are there. So then MSTs are possible multiple, because all edge weights are same. Then what happens, there is a possibility of that you duplicated that minimum cost spanning. Spanning tree means that avoiding the cycle, but minimum cost spanning tree means adding the edge weights. We are getting one particular total, that is called minimum cost spanning tree. So here some facts about the trees is already the facts, that a tree n vertices have that n minus 1 edges, already I said. So to do this one, we are using two approaches, the PRIMS algorithm. Just now I discussed the PRIMS algorithm. So the PRIMS algorithm, the greedy approach, why you call the greedy approach is we are selecting the nearby minimum. Whatever multiple edges are available to the current vertex, from that we are selecting the minimum one. So that's called, greedy. So it's a greedy approach. So remember, it works on the connected graph. Any disconnected components are there, there is no reachability, because all of the vertices, they belongs to one component, means you can build a MST. And remember that weighted edges must be there. Like we are selecting the minimum edge weights. So between two vertices, whatever you are connecting, the possible minimum value we are selecting. So the spanning tree always produce, the PRIMS algorithm produce that a subset of edges, maybe n number of edges are there. We are removing some of the high cost edges and we are including some low cost edges, which doesn't create a cycle. So that is called spanning tree. And one more thing, please see that unique solution. If weights of the edges are unique, that means no duplicate, then MST produced by the PRIMS algorithm is always unique. For example, you might have a tree with this 10, 10, 10. Then you have a multiple MSTs. Am I right or wrong? You might include first edge, you might include second edge, you might include third edge. Am I right or wrong? Because all of them are duplicate, no? Hello?
Yes, sir.
For example, you are having the values are like this: 1, 2, 3, 4. Then always we are avoiding that highest cost only. So that the possibility is 1, 2, 3 only. So always we are trying to avoid that highest cost edge is there. So that if unique values are available, the algorithm, that Prim's algorithm, it always generates a unique one. If duplicate values are there, there is a possibility of multiple MSTs for this one. So remember, already I said the steps, what exactly? The choosing the starting vertex, initialize the vertex is that weight of the particular vertex, maybe 0. Find the next connected edges, which is that minimum is there, that one we are selecting. So that we are adding continuously, repeating the 2-3 steps until all of this particular MST, but it should not form a cycle. So please look at this code. So just I quickly want to walk through that. So I said, so basically how that infinity is calculated, because the reachability of that particular vertex we are taking is just infinite. Any infinite you can take, float constant infinite you can take it. There is a widgeted dictionary is taken, distance dictionary is taken. So as I said, TE is a short form, the tree edges they are taking as a complete form. As it is, it is a list. We are trying to append that edges whatever you have visited so far. And initially, the distance we are putting as infinite, and widgeted status is false, all of them. And I says starting vertex we have chosen is 0. It does not mean that 0. You can choose any particular vertex which you want to start it from the traversal, that MST traversal. And now we are trying to extract that V and distance from U to V distance we are extracting. The distance you are updating, like whatever the distance so far is there, the distance is updated. So already 0 is started, don't worry. But in that 0, we are selecting the minimum one, whichever that, finding the minimum weights. So the minimum weight distance we are selecting, if minimum weight is there, that we are widgeting, and that particular edge is going to be the next appended one. So that its outer loop is exclusively talking about that number of vertices, that is vertices minus 1, and inner loop is exclusively that edges we are putting, and in that putting of the edges we are selecting that widgeted vertex and not widgeted one, and the distance which is available that must be less than that existing distance. So existing distance already we got infinite, definitely infinite is bigger. We are trying to traverse the first minimum one. Once first minimum you got it, that minimum we are updating it to the minimum distance. During next visit, we are selecting again another UV. So another UV. Whatever adjacents are there, in that adjacents, we are selecting the minimum. Once it is widgeted, we are trying to append it. Maybe widgeted makes it true. And whatever the edge so far we got a tuple. As I said, every time you are trying to append the tuple. See, this is the tuple value. Tuple value we are updating. That is called TE. So the full form of this one is that tree edges, and then updating that particular distances, what exactly so far it is widgeted, the distance we are updating. So update the distance of unvegetated vertices smaller than the current one. So finally the output what we are getting is 0 to 1 edge is included, 1 to 3 is included, 1 to 2 is included, 2 to 4 is included. So that's what so far. So 0 to 1 is included. I hope one more edge is missing. So yeah, 0 to 1 is included, 1 to 2 is included, 1 to 3 is included. So one more I forgot. So here one more is 2 to 4 also included. So this is what 2 to 4. This is what also included. So these are all appended into the total edges, tree edges, what you call is. So they are returning the tree edges. Along with the tree edges, if you want to calculate the total also, you can calculate. Maybe you try to append it along with tree edges. See, look at here. The next edge you are appending, no? So maybe in this particular line, you can put U, V, and D also. You put it that U, V, and D also. So the D means it's a distance value. That distance value you can calculate using another variable. Just I said it is 44 the value. That value also you can return along with tree edges. So the total tree edges you are getting along with what is the sum of this particular MST also value you can get. So this is the MST using trims. So please let me know that any clarification from your side. Is it clear? See, don't by heart the code. Please try to understand the first concept. Then you try to compare that whatever the coding line. So that don't by heart the code that it's dangerous. Yeah. So now this approach is somewhat getting the minimum and putting it. It is somewhat, it requires outer loop and inner loop. Can anybody tell that what is the complexity of this particular Prim's algorithm?
N square, sir.
Yeah. So here, look at here, the code itself, it is telling the fact. So please look at here. There is an outer loop is available. This is what the outer loop. So if you could look at, yes, this is. It is repeating up to the number of keys. What is the keys? It is nothing but the total vertices, n number of vertices. That is a fact. The outer loop I it represents. So inside of this outer loop, we are trying to extract that the keys into the U. In that U, we are trying to extract the values which are, because adjacency list, it contains that each key with the list of values. First key with a list of values. Second vertex with a list of values. What is the list of values is very simple. It's a tuple. Where it is connected, with what weight it is connected. So that's what we are getting. U is a source. V is a destination. How much weight it is connected. So there is a path from U to V. With what weight it is connected. So what happens, from the first vertex to all other connected vertices we are checking. Second vertex to all other vertices. Third vertex to all other vertices. So it's simply that it's n square. So simply the complexity when you compare it is n square or v square, because v is nothing but the number of vertices. Yeah, it is. Yeah, it is. V is nothing but number of vertices. Either n square also makes sense. But here there is no kind of easy process of it. Critical algorithm is somewhat another simple approach. So actually, one fact I want to tell you: if same graph is taken as input for the Prims, same graph is taken as input from the critical, the MST outcome is the same. You don't have the changing of any kind of output, same output. But only thing is approach is different. Let me see that the approach of this, but it looks like some easy approach, because mostly easy to solve it. It's very simple. If you could see the critical, what the critical will do is, first what it will do is, it will create sorted list of edges on weights. Is my writing visible? What I'm writing?
Yes, sir.
Yes.
Yes.
Very simple. They try to sort it all the edges based on the weights. For example, if it is sorted, what is the minimum weight edges available as? I can say this. This is the first minimum. Is it right? Is it right?
Yes,
Hello?
sir.
Yes, sir.
This is the second minimum one, because they are sorted in ascending order. And then the third minimum is going to be this one is available, this one is available, because this one is available. Of course, we can say third, fourth, fifth, something like that. Maybe that doesn't make a problem. That's not an issue. The next fourth one is going to be this in the order I'm telling you, that index positions. What you can say is frankly this maybe third, fourth, fifth. If you talk about this, is going to be the sixth. Maybe that's not a problem. This is going to be the fifth highest one. This is going to be the sixth highest. First, we are sorting it. Then take edge in increment order. In increment order, if the edge doesn't form cycle, include or append to T. T is nothing but total edges or tree edges. So we are selecting the edge which doesn't form a cycle, and we are selecting in ascending order because the particular sorting is already done. In this case, what happens, first edge what is selected? First edge what is selected out of all these are?
5 to 6.
Yes. So what it will do is fifth one to sixth one is selected because it is 5. So V is the least value. So again we repeat the process. So let me do that. This is selected over. What is the next one selected?
1 to 2.
So 1 to 2. So 1 to 2, if it is selected, it looks like this. Sorry. 1, 1 to 2. It is selected. So it's a edge weight of 6. The next one. So next one, what it is selected? Third one. Third one.
There are 3 options, sir.
3 options are there. 0 to 1 option is there. 4 to 5 is there. It doesn't form a cycle. Or 4 to 6 option is there. Maybe you select any one of this. Maybe I'm selecting this. So maybe 4 to 5 or 4 to 6. Maybe in the sorting order. Maybe they are applied that. Maybe what exactly actual order of sorting should not be discussed. Something like what you can say. Insertion sort they are applied. We don't know what kind of sort is applied. So let us you see that we are selecting another color. Maybe it is a fourth edge to sixth edge. It is not forming a cycle. So 10 is selected. So that's okay. So we have done that 5 to 6, 5, 8, 4 to 6, 10 weights, and 1 to 2, 6 weight is selected. Sorry, 1 to 2, 6 weight is selected. So the next one it is selected. Can you select 4 to 5?
No, sir.
We don't select this one. We have selected this. We don't select this one, but we have selected this. So we have selected this 1 to 2 also. So far we have selected edges are, so 5 to 6 is selected. Then 1 to 2 is selected. Then 4 to 6 is selected. But we don't select this 4 to 5 because it's forming a cycle because of cycle. For example, 4 to 5 is selected, we don't select 4 to 6. Make sure that, because while you are selecting, we go in increment order. If it doesn't form any particular cycle, we are including it. So
Sir,
the next one.
In that case, the weight will be more, no, sir, from 4 to 6.
Yeah, 4 to 6 if you selected, there is no possibility of 4 to 5 selection. Is it right?
Yes, sir. But if we select 4 to 5 means
Then we 4 to 6 cannot be selected.
Then the weight from 4 to 6 via 5 will be more, no, sir.
No. If you see, look at here, sorting order we are selecting. 5 is selected, 6 is selected. Selecting this 10, we have 3 choices. First 10, if you select 4 to 5. Second 10, can you select 4 to 6?
No, sir.
You can. But second 10, you can select this 0 to 1.
Yes, sir.
You can select because it doesn't form a cycle. 0 to 1 is okay. But This is not included because already we have included 4 to 6. No possibility of including 4 to 5. So this particular one is already done. Because similar edges are there, similar edge weights are there. We select a edge which doesn't form a cycle. For example, before me, somebody is already selected. If I am adding into that, maybe I am forming a cycle, so I should escape it. Is it right or wrong?
Yes, sir.
But
But
what sorting is applied? Tell me.
the minimum condition will be not to here, no, sir.
Yes, see, we are selecting the minimum one only. Minimum edge only we selected, but that edge is included if and only it doesn't form a cycle. Is
Yes,
it
sir.
right?
But yes, sir. But if we select that 4 to 5 age means, then from 4 to 5, 4 to 6, it is weight of 15, no, sir. It is less than 10.
No, I don't understand. 4 to 5, 5 to no, no, don't think it's a single source shortest path.
Okay, sir. Okay, sir.
Please avoid that single source shortest path. What exactly the cumulative total of all edges is the total. Clear?
Yes, sir.
Fine. That I hope that is only maybe that's what maybe you are thinking from 0, you are thinking from 1 or something. That's not right. Yeah. So this is okay. After that, this 0 to 1 is included. Okay, fine. So that I'm using this one also included. So then after it, what we are selecting is next minimum. We have a 20 choice, we have 18 choice, we have 70 choice. Is it right? Out of these three, 18 is the minimum. Can we select 18? That is 0 to 2.
No.
Because
It forms a cycle.
yes, it is forming a cycle. We don't select it. Because one cycle is created, we are avoiding the tree property because we are creating spanning tree. Tree should not contain the cycle. So can we select 1 to 2 to 3? There is no choice because we must select it. The next hierarchy as per ascending order is that 1 to 4 must be selected. Am I right? Because 18 is avoided,
Yes.
1 to 4 must be selected. No? So that we are selecting is 1 to 4. 1 to 4. So the last one is there is no choice. 2 to 3 must be selected. 2 to 3. So 5 to 6 is weight of 5 to 6 is weight of 6, and 1 to 2 weight is that 6. Sorry. So this is 5, this is 5, and 1 to 2 is 6. 4 to 6 is 10. Is it right? 4 to 6 is 10. 0 to 1 is 10. 1 to 4 is 20, and 2 to 3 is 70. So the total is going to be 5, 11, and then 21, 31, and then 51, and then this is 121. This is the total. But thing is, somebody got it out. If I take this crystal algorithm, I applied it, so I got 121. If on the same graph, if I applied prims, am I getting this 121? Yes. Let's try this. Is it clear? Because
Yes.
whenever you take a same graph input to two different algorithms of prims and crystal, the output could be same. Let's try that. So as per the particular prims algorithm, we are taking three edges is empty initially. Maybe initially it's an empty list. Let me start it from here. You can select any of the starting vertex. It doesn't make a problem. Maybe you can select 2, you can select 1, whatever it is. From the 0, we have an adjacency of 10 is available, 18 is available. Which one you selected?
10.
TE we are selecting is, we are selecting first edge is going to be that. So first edge we are selecting is 0 to 1 we are selecting because it is the minimum out of these two. And the next one we are selecting from the 0 to 2 we have a 18. From the 1 to 2 there is a 6. From the 1 to 4 there is a 20. So out of these three, which one you selected? Out of these three. It's
1, 2,
already
2, 6.
it's already done. It's already included. So out of this 0 to 2, 1 to 2, 1 to 4. So out of this we are selecting is that. So 1 to 2. Is it right? 1 to 2, no? Which is the minimum?
Yes, sir.
Hello? So we have selected this one. So next one. So we have that 0 to 2 is available. So we have that 1 to 4 is available. Out of these two, can we select 0 to 2?
No, sir.
Because it is forming cycle. So we cannot select it. So next one is we have a choice of that 1 to 4 is available. 2 to 3 must be selected. There is no choice because 3 must be included in the MST. So out of these two, definitely the next one we are selecting is 1 to 4 only. Of course, 2 to 3 also included, don't worry. But now from the 4 to 5 we have 10 is available, 4 to 6 we have a 10 is available. So we are selecting the next 10, maybe 4 to 5 you are including. So once 4 to 5 is included, this is included. So 1 to 4 is included. We don't include 18. So next one, 4 to 5 we have included. Maybe it is 10. So next one we are having 2 to 3, it must be included, but no issue because it must be attached into this particular tree. Again, 5 to 6 is available, 4 to 6 is available, 2 to 3 is available. So out of these three, we are selecting that 5 to 6 because it's a smaller value. 5 to 6, it is not forming cycle also. We are selecting 5 to 6 so that this 5 to 6 is included. Can we select 4 to 6?
No, sir.
So that we give possibility. So we don't select this 4 to 6. But we must include 2 to 3 because the edge must be connected to the tree, which doesn't form a cycle. So that we got these edges. Now let me add it. What is the total? This is 0 to 1 is 10. So 1 to 2, 1 to 2 is there, that's a 6. And then 1 to 4 is available, that's a 20. 4 to 5 is available, that's a 10. Next one we are having 5 to 6 is available. Where is my 5 to 6? Yes, my 5 to 6 is available, it's a 5. And the next one is 2 to 3 is available, that's a 70. Now let me do that. It's a 16. So that is 36, 46, and then it is 51, and 51 it's going to be 1. So we got the same value which you applied. So when you are applied the same graph you have taken as input from the critical, and same graph you take for the prims also same. So because maybe this could be one kind of quiz question. So they'll give you one quiz statement. Let's take a input tree or a graph G. You are given an input for that algorithm T1, T2, where the T1 is the critical algorithm TK, where the TP is the prims algorithm, traversal prims. So the outcome which you are resulting for the TK and TP is same. The traversal critical and traversal prims is same. Yes. So maybe true or false statement they are giving multiple. So
So,
tell me. Hello.
so is it based on the edge weight or the vertices, sir?
Completely edge weights only.
Okay, sir.
Completely edge weights. So, but whenever same graph input you take it, same output will come. Clear? But only
Okay, sir.
approach is different. See, look at the approach is the critical algorithm is somewhat simple approach. See, very simple approach. Sort all the edges. The step number 1 I'm talking about. Sort all the edge weights. So, and the graph in the non-decreasing order, maybe it's increasing order. Create a new empty list, which is called, TE. I'm taking it as tree edges or traversal edges. So we are iterating through the sorted edges, starting from the smallest weight to highest weight, because 0 to n minus 1 edge weights are there because they are in increasing order. So for each edge, check that adding that into that MST, is it creating cycle? If it is creating a cycle, we don't include in MST. That's what If the edge doesn't create a cycle, then include in MST. If it creates a cycle, don't include in MST. So repeat these 4 and 5 steps continuously until all of the edges is covered. So it's a very simple code comparatively the critical. See, as I said, uh, each one component and TE is a traversal edges, component is one particular dictionary, edges which are that list of edges are included. So initially what they did is they have taken a tuple. Please remember what they did is, do you know tuple sorting? Whenever you sort a tuple, first the tuple is sorted based on the first value. Am I right or wrong? Am I right or wrong?
Yes, sir.
So
Right.
that the
Right,
first
sir.
tuple value should be that distance. So that's the reason they try to convert that whatever that adjacency list you have given it, that they are trying to bring that distance as the first value of the tuple. So that's what this DUV instead of UVD, they made it one particular local edges, which is that DUV from the adjacency list they are taken. So the component name they are making it is U from where you started each particular component. What you call component is, don't worry. The next 6th week introduction, it starts from components only, what you call union and find data structure. Then I will talk more about component. Don't worry, what really the component is. So it is simple. Actually, still you want to include it. So what really the component is? See, look at here. So each particular edge is called one component. See, what is this one? This is one component. This is basically one component. So once that another component is added, your component size is increased. Another component is added means your component size is increased. So that is called component. So anyway, detail things we'll understand components in the 6th week of lecture. Immediately we'll jump it. So listen, we are sorting. Already I said sorting based on the edge weights. Now we are trying to traverse the edges. So here U to V, which does not form a cycle. So if it is forming a cycle, U to V we are adding, is it forming a cycle? If no, then only we are appending it. Then only we are appending it. If it's forming a cycle, we don't append it. Simply the components are added, the edge weights are added, the total edge weight you are getting. So here also same, 5 to 6 edge we got it, 1 to 2, 0 to 1, 4 to 5. Of course, along with this particular one, we want to bring the distance also, means simply create a local variable, the total sum. The sum is added with distance value, as and when T is appended with UV, we try to add one more calculation, that is, sum is nothing but sum plus D we are adding. Along with TE, we try to return that the sum also. So then you get it. So here also, the complexity goes to that n square or v square. Because see here, as I said, sorting complexity still now, any even merge sort they applied that internally the Python system is using, the merge sort complexity is always, it is n log n. Am I right or wrong? It's all cases. Hello? Is it right?
Yes,
Yes.
sir.
So that's okay. That's the least one comparatively n square. But here we are applying again the outer loop, that is number of edges we are walking through, and in that particular edges we are trying to walk through that each key. So each key we are trying to traverse it, so that how many edges are there, we try to get that each edge, whether this particular edge include or not, whether this particular edge is include or not. If you are able to include that edge, then we are trying to add particular component into the, that vertex into the components. So you will understand what really the component is. Basically that it will start it from 6th week onwards. This is two particular MST algorithms. Yeah, Dhanvantari, you want to ask something?
Yes, sir. I want to ask that what is the extent you have?
Yeah, extent is nothing but append only. Only thing is both of them are same. So only the coding, another syntax of it. Append and extend is same. Clear? Yeah. So this is about it. Before going for the 6th week, actually, one particular concept in the 6th week, it belongs to that 5th week only, but due to that more kind of content in the 5th week, they started in the 6th week. They start to include that concept in the 6th week. This particular starting concept of the 6th week, it belongs to the 5th week optimization only. Let's jump into the 6th week. So is my screen visible? Give me
Yes,
one.
sir.
Give me a 1 second.
Yes, sir.
I'll join it. Join in few seconds. Yeah. So look at here. So 6th week major concepts are belongs to that trees only. Week number 6. So the major part of this week 6 is trees. But actually, I may not cover all the particular concepts of this particular week 6 because some part already we spent some time on the pending concept of the week 5. Maybe some part of pending is there, the week 6. We'll cover because maybe we have upcoming quiz 1 that's more important. We don't want to spend much time on that. But there is a minor concept is included here. Another one that is called union find data structure. Union find data structure. Remember, it's a data structure. It's not an algorithm because algorithm is a standardized procedure. Like Prim's is algorithm, Krishkal is algorithm, Bellman Ford is algorithm. But linked list is a data structure because linked list is the way of organizing of data. So that linked list will help to somebody else. Stack is a way of organizing of data. That stack is helping to DFS algorithm. Q is a data structure that is helping to BFS. Am I right or wrong? So here,
Right, sir.
first we'll finish up that. The first major concept or initial concept is union find data structure. Union find data structure. So the importance of union find data structure is why it came to the screen is to improve the complexity of time complexity of Krishkal algorithm. So already we know that Krishkal algorithm complexity is O of n square. N is nothing but so number of vertices. Can we improve better? So using union find data structure, we can improve little bit. We can improve it because it is helping to Krishkal algorithm. Yeah. Hello.
So what is the time complexity of crystal, sir?
N square or V square because number of vertices. Same. Prims and Krishkal is both of them are same. O of n square or V square. Okay.
Okay, sir.
But using union find data structure, some part we can improve it. So here we started because somebody already we said about component. Now let us we understand what really union find data structure. See, union find data structure, it's an abstract data type. We build a new data type. So somebody thought how to build a new data type. It's very simple. The object-oriented programming in Python, because already you know classes, objects, all these are the same particular implementations we do. You know, class contains data members, methods are there,
Yes, sir.
constructors are there. So using it, we are creating a new data structure called union find data structure. Now let us we see that what really union find data structure is. So the major part of it, the first part of the union find data structure is set of vertices are partitioned into singleton components. So don't worry what exactly the singleton component. Each particular vertex, it belongs to one component. For example, so let you see that there is a graph 0, 1, 2, 3. This is a graph. So this particular union find data structure, what it will do is each vertex is considered as a one component. This is component 0. This is component 1. This is component 2. This is component 3. So each one is individually one component. That is called, singleton component. Each one belongs to its own component. Where is my 0 is available means 0 is available as a 0th component. 1 is available as first component. 2 is available as. So one individual component, each one is considered. A set of elements, a set of vertices are partitioned into singleton components. Now, what exactly is? For example, how to do this partition is, I want to use a simple dictionary. Can use a dictionary, So maybe 0th vertex belongs to 0th component. First vertex belongs to first component. Second vertex belongs to second component. Third vertex belongs to third component. So this is how really the singleton component it looks like. Now my question is, how to find the component, the particular vertex component? What is the time complexity? There is a find operation. The next operation we are going is the find operation. The find operation. What is this find operation? It will return the component that the vertex belongs to. For example, I say that find, there is a method, maybe, I'll write one method, maybe, find method. I'll call that second vertex belongs to which component. So it will return that 2 or not. Is it written 2? Is it
Yes,
written
sir.
2 or not?
Sir,
What is the time complexity of this find operation?
we
Time complexity. 1 unit of time, no? Because dictionary finding key and value is how much?
okay, sir.
So the time complexity of this find operation is O of 1. O of 1. Is it right?
Yes,
Is it
sir.
right?
Yes,
Yes,
sir.
sir.
So finding operation of the particular one is just you are going to return the particular one. Simply that. The next one is, so here the next one is third operation. So first operation we said that set of vertices are partitioned into the singleton component. Of course, sorry, this one also requires component, so complexity. So making that singleton component, building a dictionary from a graph, definitely it requires some type of complexity. Maybe it requires that a linear time. Is it right? Because building
Yes, sir.
all particular vertices, if n vertices are there, we are making n components. If 10 vertices are there, 10 components, so that we can say that it is linear complexity. Find operation requires that unit of time. Third operation we are implementing. So this is the union operation. The union operation, what it will do is, it will update the union of u and v. What it will do is, it updates it updates so what you can call update or merge, what you can call merge. So u with v. So simply what exactly the element U is added into element V component, V's component. So don't worry, maybe you may not understand this English sentence, whatever it is. So simply, I'm trying to merge, I want to make a union, both of them belongs to that. U will be merged with V. So let me go back to this one. Now, is it a singleton components? Because 0 belongs to 0 component, 1 belongs to 1, 2 belongs to 2, 3 belongs to 3. Now, what I do is, intentionally what I did is, I'm calling a union operation. What I did is, I want to merge first vertex with third vertex. First vertex with third vertex. So, first vertex is U, third vertex is V. What happens, 1 and 3, now they are independent components or singleton components. After this union operation, they belongs to one component. Did you understand? They make it a union. Do you understand?
Sir, then what is common name, sir?
They are combining, they are merging, they are put together into a single component. Instead of singleton component, they are putting into the single component. Is it clear?
Yes, sir.
Now still I am going with some example analogy. For example, you have books, box number 1 is having book 1, box number 2 is having book 2, box number 3 is having book 3. So what I'm trying to do is, individually each one is a singleton, single box contains one book. Intentionally what I'm doing is, I'm taking the second book from the box number 2, I'm putting into the box number 3. Hope you understand. Is it clear? Is it clear?
Yes, sir.
Now what happens, the box number 2 is empty because no book is there. Now box number 3 contains second book and third book. Am I right? Am I right?
Yes, sir.
So this what happens, this union operation, what it will do is, if for example, I did this union of 1 and 3, immediately what happens, currently the first element is available in the first component, it will be changed into the component number 3. So anyway, 3 is in third component, 1 also available in third component. Is it right? Is it right? Is it right?
Sir, that value means the common name, sir.
This is the vertex or element. What you can call element or vertex. This is that component number, which component it belongs to.
Okay, sir.
Clear? So by default, each one is a singleton component. After union operation, U will be merged with V. So U is right now what? 1. I'm trying to merge with element number 1 with element number 3. So what happens, element 1 vacates the component 1. It will join with component number 3. So now the component 3 contains 2 vertices. Vertex 3 is available, vertex 1 is available. Is it clear? Is it clear? Hello?
Yes, sir.
Now, my question is, so whenever one particular union I'm telling, like U, we are merging with V. For example, we are doing sequence of M union operations. M union operations. M times you are calling the union operation. One union operation complexity is how much? You're trying to merge that U with V. That means definitely you need to search for the V and we have to replace it. Is it right?
Yes, sir.
So M times you are doing union operation means definitely the complexity goes to O of Mn or not.
Yes,
Is
sir.
it right? Is it right? Hello? Hello?
Yes, sir.
So that is what the theoretically they want to describe. Please look at here. Please open that, what I discussed is so far is theoretically what is this union find data structure. So maybe the, the names of these things is different, but concept is same. See, look at S is partitioned into that set of components. S is nothing but it's a graph. Let you say that a set of vertices. Component 1, component 2, component 3. That's nothing but element 1, element 2, element 3. Each S, it belongs to the S exactly one component, which is called singleton component. Singleton. So initially, we are making a making union, which is that each particular vertex, it belongs to one component. That is called initial setting. Then finding particular vertex, which component it belongs to, is a find operation. And union operation is, as I said, U and V, they said it is S and S dash. I said U and V, they said it is S and S dash. Oh, sorry, here it is a printing mistake. It's S dash. So we are trying to merge S with S dash. There we try to merge U and V. Both of them are same. This is what the union find. Please look at here. As I said, it's an abstract data type. How to build abstract data type is very simple. We are trying to create classes and objects. So what they did, they are creating one dictionary. The size parameter they have created, size is nothing but initially it's 0. So I said each of them complexity. Making union operation, this operation is singleton components we are building. Each particular component vertex, it creates the component ID. As I said, it's a dictionary. So 0th one, it belongs to 0th component. First one belongs to first component. Second one belongs to second component. To build this, the complexity of this make union operation is how much? O of n complexity. Yeah, somebody wants to ask something. Yeah.
Sir, on what basis that union is happening, sir?
No, forget about union. First, let us go step by step. First, make union operation. It is initial setting. Initial setting is singleton or not?
Yes, sir.
That is okay. This part is okay. This part is clear.
Yes,
Building
sir.
a dictionary, singleton components. Yeah.
Yes, sir.
Now, find operation. As I said, 3 operations we are talking about. First operation is clear. Second operation is searching a particular key. Searching a particular key is a unit time operation, which is O of 1. It's a linear time, make union find. This is only unit time. Is it clear?
Only if it is a dictionary, right, sir? If
Yeah,
it is a
because
list.
dictionary finding key is unit operation, no?
Yes, sir.
Python dictionary. Clear? This is clear? This is clear? This step is clear? Hello? Hello?
Is it clear, sir?
Yeah, this vertex belongs to which component? That component value it returns. Component value means 0, 0, 1, 1, 2, 2. That component it belongs to. So now, here it's a third operation. As I said, U is merged with V. Is it right? U is merged with V. Now, the old component is this U. New component is this new. I said U is merged with V. S is merged with S dash. So now we are repeating a loop. What is this loop is doing? Until the size. What is the size? My particular components of vertices. Is it right? The total vertices, no? 4 vertices 4 times, 3 vertices 3 times. Is it right? Is it right?
Yes, sir.
Now, this loop is repeated, searching for the components. Wherever this old component is found, that is updated with new component value. So I'm searching for the U. Maybe the U is available in the first location. Maybe I'm trying to do that union operation. U is 3 and V is 0. What should I do? I have to search for this one. Is it right or wrong? I have to search for that one or not? Hello?
Yes, sir. But
Ah,
how
after
we
se-
get
ah, after
how,
searching, we need to replace After searching, after you found that component, we need to replace with new. Okay, tell me now your question is.
How we determining that 3 needed to be combined with 0?
See, this is what u and v, you are telling a parameter. The component value we are getting of the u, the vertex u component value are getting, the vertex v component value are getting. Is it right?
Yes, sir.
See, the book number 0, we want to merge with book number 3. So what we do, the book number 0 component value are getting is C old. The book number 3 component value are getting is 3 box number. Is it right?
Yes, sir.
That box number is updated with K, because K is nothing but the searching one. If the old is found, immediately replace with U. Is it clear?
Yes, sir. So we are getting U and V from the outside.
Exactly. This is U and V you are taking as a parameter.
Okay, sir.
That particular vertex component value you are getting. That component value we are finding. If the particular value is found, immediately it is replacing. So what happens, this particular find operation you do sequentially. One time you do it means n complexity. If m number of times you are doing operations means it is O of m into n. Is it right?
Yes, sir.
See, what I do is initially each one is a singleton component. First I will merge 1 and 3. Then I will merge these 3. Is it right? Is it right? Hello? Hello?
Yes, sir.
Then I will merge these one. So now all these 4 are belongs to one component. So to do this merge operation, sequence of union operation, I have to call it. So sequence of union operation, you need to call m times. So definitely it is that O of mn. This is a naive approach. What you can call, a simple kind of approach. There is the improved version is that. See, look at improved version. So they talked about it. Yeah, this is improved version. So in this, what they did is interesting thing, just few changes. See, what they did is here they are taking additional data structures, what you can call, local data structures. They're taking a members dictionary. What it contains, it contains that the component is a key and a list of vertices. Does the component it contains. So because I said component is nothing but a box. Is it right? Is it right? The box number 3 contains 0th book is there, 3rd book is there. Is it right or wrong?
Yes, sir.
Hello? So this way it will maintain this another dictionary called elements. This is a new dictionary they are introducing. And still there is another dictionary they are making. So earlier size is single one. Now size also they are taking as one dictionary. What is the dictionary? It is, the component is a key and size of the component. It's very important. Why should I tell you this size is very important? So another component and its size. See, this one I'll tell you why they are maintaining sizes. See, I want to merge that 2 elements into a single component. Does my box requires bigger size or not? Does my box requires bigger size or not? I'm trying to merge that 0th element to 3rd box. Does my 3rd box should have a capacity or not?
Yes, sir. Yes, sir.
So that size is also tracked. The size is also tracked. And the members, how many particular members are there in that component, that is also maintained. The members list is maintained. How many members are there also maintained. So this will help you to improve its complexity. So how it is helping its complexity, you see. So this they are maintaining as a dictionary. Earlier it's not a dictionary. Here members is a dictionary, size is also taken as a dictionary. Now these things, components. So of course components you already know. These two are additional dictionaries that take. So as I said, making union find, each vertex it is traversing. In this, we are making components, that is as usual. But members, what they did is, we are making initially each one is a one single list. Initially, each component it contains a single list of element, because square bracket they are using. And size also it contains a one value, because singleton is a default. So the complexity of this one is that it is simple complexity, that is O of n complexity. And find operation also unit of time. Is it right? Unit of time or not? Find operation is unit of time. Is it clear? Is it clear?
Yes, sir.
Now, this union operation is somewhat interesting. Earlier, if you see, always we are trying to merge U with V. Is it right? U with V you are merging, no? You are merging U with V. Is it right?
Yes, sir.
Now, we don't merge always U with V. We try to merge the smaller component with the bigger component. Smaller component with the bigger component. So what I do, you see that. See, look at here. We are taking old component. We are taking new component, which is similar to the previous naive approach. But here, if new one is greater than or equal to the old one, then we try to append with new. For example, old one is bigger than the new one, then what we do is we are appending old with new, reverse. Either old one is merged with new one is merged with new. So that what happens, either it goes that this if condition or this if condition. The old one is merged with new one is. So what they want to tell you is, for example, so you are having a components like this 0, 1, 2, 3. Let's assume that you are applying this make union operation on the Kruskal's algorithm. So whenever you are applying the Kruskal's algorithm, so it is n square complexity. So we want to reduce it somewhat better complexity. We try to use make union find operation. What they are doing is, maybe this is what your particular singleton components are there. So it doesn't form a cycle, then only Kruskal's is going to be added. First, maybe these two are combined. Next, maybe these two are combined. Next, maybe these three are combined. Maybe something like this. So what exactly, whichever is higher, the lower one is merged with higher one. So for example, if you recall your Kruskal's algorithm, maybe something like, Kruskal's approach is this. Yes. So basically, this is, Prince, sorry. This is Kruskal's. We are taking the first component, maybe 4 to 6. Second component is 5 to 6. Next component you are adding 4 to 6, because it is not forming cycle. Now we are trying to merge. This is a bigger component. This is a smaller component. Am I right or wrong? Am I right? Because these two belongs to one particular component. These three belongs to one component. Who is merging with means this 1 to 3 is 1 to 2 is merged with this component or not? Is it right?
Yes, sir.
So that is what, either smaller one is merging with higher one. So either you are going this if side or else side. So whenever you are going either one of them, definitely that means one thing you lose it, one thing you benefit it. What do you call this? So this particular approach is, it is making the union operation is log n operation, because just like your binary search, either you are going that left of partition or you are going to the right of partition. So we don't need that mn complexity. O of mn complexity is not required. We require that log n complexity. Always lowest component is merging with highest component. So that is what the approach we are applying. So that's the reason we try to have that complexity somewhat reduced to the log n. Due to that, see here, improved critical algorithm, they did not change the code. Whatever the code is available here, the same code is copied. See, I'm telling you, make union is not a new algorithm. It's a building a data structure. It is helping to critical algorithm. Now, same data structure they are taking. So they are not changed any code. Same, nothing is changed, just copied. Now they are improving. What way they are improving critical is, see that here. First they are making make union, which is a linear complexity O of n. Now, sorry, it is creating these two steps because it is creating class object. Now make union operation, which is singleton components you are creating, which is linear time. Now there is a union operation they are doing, make union u to v. So whenever they do that union operation, it is going to be the log n complexity because you are using improved version of this one, improved version of this. So it's a log n complexity. Now what happens, rest of things are same. So whatever, component size, bigger size is there, smaller size is there, that is same. So the improved complexity is this. So the complexity is tree has that n minus 1 edges. The overall union operation is O of n because it is that. See here, amortized cost. Amortized means the one thing you lose it, one thing you benefit it overall. Like, one way you benefit it, one way you lose it. But here one more sorting operation is available. Hope you know that the sorting operation is n log n. Am I right or wrong? Sorting operation is there, no? Because critical algorithm requires sorting. So in this sorting, equally it is sorting, it takes that n log n or m log n. So equivalently what you say that? So n log n, since m is less than n square, but overall time is, the overall time of the complexity of this one is, so m plus n log n, which is definitely less than n square. We cannot say that extreme high performance improvement is there, but it is somewhat improved. The complexity of this overall improvement is this one. This is what improved, which is definitely less than n square. Is it right? We are taking the help of union find data structure. Using union find data structure, the critical algorithm, somewhat it is improved. So that is called amortized. So even you can check your dictionary meaning of it. One thing you lose it, one thing you benefit it. Either if side you go, L side you go. So if side or L side, either one of side only you are going. So that due to that you are getting the operation takes that it is log n operations only. Sequentially, if you do that log n operations, it is going to be the n log n. Already sorting takes that m log n. So the overall complexity, if you say that it is m plus n log n. Hope you got it. Is it clear? Is it
Sir,
clear?
can you please repeat that?
Which one?
The last one, sir.
Yes. So this one?
Before that.
Yeah, here it is. It is clear.
The combination of two components, sir, based on that size.
Wait. So just a minute. Let me close it. This one. Yes. Here it is.
Yes, sir.
This is up to it's clear. Up to this clear.
Yes, sir.
Now we are applying.
Till installation, sir. After installation, it's like complicated.
This is creating the class object. Is it right?
Yes, sir.
Fine. Now we are creating singleton components because it's a linear operation. Is it clear?
Yes, sir.
Now, so it is forming a cycle. If it is not forming a cycle, the same condition, whenever it is not forming a cycle. So what exactly simple? See, I'm creating singleton components are there. 1, 2, 3, 4, maybe something like this. We are having the edges, maybe something like this. Maybe you are having this one, maybe maybe it's there. So whenever you are trying to include edge, make sure that it is cycle is not formed. This is clear? This line is clear?
Yes, sir.
Now, union operation you are doing. What is this union operation? It is merging U with V. Either U is merged with V or V is merged with U, because based on the if condition. Is it right?
Yes, sir.
Fine. So now what happens, out of this, maybe smallest one, maybe you think about this. These two are attached as one component, maybe based on the least value. Is it right?
Yes, sir.
Is it? So now what happens, these red color indicates that one component. Next time, next minimum it is selecting, no, because it's already sorted edges. It's a sorted edges, no? Clear?
Okay, sir.
So when it's sorted edges, maybe next time it is merging these two. Sorry, these two have been converted as a one component. Is it right?
Yes, sir.
Now, third time what it is doing is, it is creating this. Is it clear?
Okay, sir.
Now, this third one joined with this, maybe this is, C1, maybe this is C2. C2 is a smaller size, C1 is a bigger size. C2 will be added to C1. Is it right?
Okay, sir.
So that it is expanded here. So what happens, instead of going this union operation with a single stretch of for loop in all cases, you are trying to traverse either bigger component only. We are trying to traverse. We are trying to merge the smaller component with bigger component. Traversing the smaller component requires lesser time. See, look at here. So whenever you are trying to merge old component with new, we need to traverse only old. Is it right?
Yes, sir.
Whenever you are merging new component with old, we need to traverse only new, because new is a smaller one. So that it is amortized log n complexity. Up to that, it's clear, no? Clear?
Yes, sir.
Now, now the minimum size only you are selecting. As I said, the sizes you are selecting is the minimum, because the component sizes, which is the smaller one. So whichever, see, when do you stop the process? If total vertices, see here, the component sizes are increasing. Like initially it is started with this one, later it is expanded to this, later it is expanded to this. Once all of the vertices are over, see, look at here, this is what the condition. If the size of the components available in U, if it is greater than V, because U is merged with V or V is merged with U, all particular vertices are included in U component, or all vertices are included in V. So if that is happened, immediately we'll break it. Either U is reached to the maximum size or V is reached to the maximum size. Then we are stopping it. That means all vertices are union operation is done. Is it clear?
Yes, sir.
Now, the complexity, it makes a difference. This is a linear time, because making a simple dictionary with traversing of all, and the sorting complexity is there, that is m log n. Maybe differentiate between n log n and m log n, they are using m log n. This is the particular one is a union operation which is amortized, because n times you are calling log n times, we have to do that n times, so that is n log n, that is m log n. Simply it is overall complexity. When do you say that? M plus n log n, which is definitely less than, somewhat less than, or equal to n square. So that it is nearby value, but definitely it is less than. Is it right?
Yes, sir.
So that it is improved complexity, so that make union find operation is helping to the critical. So critical algorithm is not changed, only we are taking additionally abstract data type, that is called union find. So this concept, it belongs to simply, fifth week only, but only thing is it is helping to the fifth week. This is one starting concept of week 6, and after that all concepts in the week 6 are different. Again, new algorithms are introduced. Up to this, is it clear? Is it clear? Yeah, just you raise up hand if any clarifications are there. Otherwise, just you give me a thumbs up. So otherwise, I'll go for that major concept of the 6th week. I'll introduce. Any doubts? Any clarifications? Shall I proceed for the next? Yeah. So one more thing, somebody may get a doubt. So in the OPP examination, do I need to implement the union find data structure? No. They'll give you prefixed code of union find data structure. They'll give you prefixed code. Only thing is you need to implement that particular critical algorithm with help of using of union find already available. So you not build that entire code. Only you understand the concept of union find. Prefixed code is available. You try to use it. So that things only they'll ask you. If they don't want to optimize the critical algorithm, they directly ask you in the OPP examination, straightforward critical algorithm. Then we don't try for better complexity of critical. We leave as it is the implementation, that is O of n square. This is what a simple outline of the union find. Okay, shall I go for that? Yeah.
Sir, which part
Yeah.
of our
Das.
syllabus are important for OPP?
No. Critical algorithm is important. Union find is not much important. Critical algorithm alone is important. Is it clear?
Okay, sir. Okay.
Hello.
Yeah, yes.
Right. So I'm jumping to the major concept of the week 6. So now the next concept what you are learning in the week 6 is completely a different one, and next part of entire week 6 is based on the trees only. Trees. See that tree is basically, it is having the, sorry, I'm sorry, one concept I missed it. I'm sorry. Before going for the trees, there is priority queue. Actually, they did not. They it's not very important, but there is a overview is given. Priority queues. Can anybody tell about the queues? Queues.
First in, first out.
Exactly. First come, first serve is there. So whenever first come, first serve, actually, it is FCFS1. But the priority queue, what it will do is, each element associated with a priority number, the priority number. Let's assume that highest priority number, maybe it represents the highest token number. Lowest priority number is called as lowest token number. Maybe you are having a doctor appointment, you are having the sequence of token numbers. 1 is the highest priority, 2 is the next priority, 10 is the lowest priority. Maybe something you can consider minimum value is highest priority or maximum value is highest priority. The choice is yours. So let's assume a case, highest number indicates higher priority. Anything, maybe lowest number you can create is the lowest highest priority, that is your choice. So as per my case, it is making highest number indicates that highest priority, what you can call as. So here the priority queue, what it will do is very simple. As and when you are adding the operation, because generally we do that NQ operation, is it right? And DQ operation on the queues. So whenever you do that NQ operation, we add the element and sort it. What is the sorting complexity? What is sorting complexity?
Log n.
Exactly. So n log n, is it right? n log n.
Yes, sir,
It's
in
not
log.
log n. So n log n. So if you do in that way, I want to do that, process that highest element is first, so that processing higher priority one, higher priority is first. Maybe what you can call as delete max. Delete max. What is the time complexity for delete max? Deleting the maximum element.
If it is in last, it will take a constant time.
No. Let you consider it is highest number indicates highest priority. We sorted in descending order
An order of one.
because I said it is higher number indicates that highest priority. Maybe if you consider lowest number indicates the highest priority, then you don't need descending. So what is the complexity of delete max?
Order of one, sir.
X. So unit of time. So that here, so simply unit of time means maybe pop operation they are calling the stop element that it is. So here the main priority queue job is that every time we try to process that higher priority element first. So generally the applications of priority queues, operating system when it wants to process that list of jobs, it will process based on the priority numbers. Maybe operating system have some reserved jobs like garbage collection and freeing the memory space. All these are the first priority jobs. It will process that particular jobs are first. Later it will do that other particular jobs later. So in that case, the priority queues are used. So actually, in this one, just they talked about only overview. They did not talk about any particular implementation. So just it is for understanding. Need to maintain a collection of items with priority to optimize the following operation. What operations they are trying to optimize? That is this one. So highest priority element they want to process first. How can I do that? If and only that is sorted. Then you can process it with unit of time. So need not be unique because two particular highest numbers are there. They can be in descending order. Two kind of lowest numbers are there. They are in first. It can be. So adding element into the list is simply appending the list. What exactly adding or NQ operation. But to maintain the priority queue internally, you're supposed to execute n log n sorting complexity. But they don't mind about n log n. They always worry about are you giving the priority to the VIPs or not. That is what they are taking care about. So that is always we are trying to making them to front of the list and we try to process it. So this is about the priority queue, but there is no implementation. Don't worry. Only it's a theoretical definition. Now we are jumping to the trees. Tree, which is what we can call it is that it is a cyclic graph. It's a graph, but no cycle exists. But one few properties of the tree is what the tree is a root with children or descendants. Descendants are available. So if the descendants are two descendants maximum, two children maximum, two descendants or two children maximum is called binary tree. Binary tree. See that if you could say that, is it a tree? Is it a tree? Is it a tree or not?
Yes, sir.
It's a tree
It's a
because it
tree.
is not creating any kind of cycle. It's a cyclic graph. It's a tree. So, but if it is having at most two children, at most two, not more than two. So, for example, again, one is having 3 and 4. So, this is called binary tree. Binary tree. This is called tree. So, hope you got the differences. Is it clear? At most two. So, now one more example. Is it a tree or binary tree?
Is it a tree, sir?
No, it's a binary tree at most. At most means either you can have one, none, or two. Is it right?
Yes, sir.
You might have one, none, or two children. Every root is having either one or none or two. For example, this is a root. How many children are there? Two
Two.
children. Is it right? Is it right?
Yes, sir.
If this is a root in this level, how many children is there? Two. If this is a root, how many children are there? None. Is it right?
Yes, sir.
So binary tree is at most two children. Tree can have any multiple children, but we don't worry about the trees. We always worry about binary trees only, because binary trees are easy to organize and there are many applications are there is about the binary trees. Up to this, is it clear? Is it clear? Anybody have any clarification about this trees? Okay. Yeah. Okay. Fine. So now some more extension part I'm going. So what is the extension part I'm going is, so now another property of the tree is height of the tree. The height of the tree is, yeah, that's it. Height of the tree. Height of the tree. Let me consider a tree like 0. Let you consider it's a tree means binary tree only. By synonym or by particular technical communication, I may say tree, tree, tree. Please consider that's a binary tree. We don't talk about more than two children. We always talk about less than or equal to two children only. So this is a one tree. For example, we can consider this. One is having again two children, the name called 3 and 4, and 3 is also having more. 4 is having one child, it's called as 5. Now, what is height of this tree is, this is level 0, this is level 1, this is level 2, this is level 3. Because when you go to that top to bottom, the level of the tree is improved. So if you could see that the level is improving because the root itself is not having any kind of height. To reach from 0 to 2, the height is improved to one more step. Is it right or wrong? Plus 1 is done. Is it right? One level we go to the next. Similar way, from the first level to second level, one more edge is added. One more level of edge is added or not? Hello.
Yes, sir.
So from this level 2 to level 3, one more edge is added. So that the height of the tree we can consider it is 3. The height. The root alone, it contains what is height means just nothing, because your root is standing on the floor. The root is standing on the ground. It does not have any height until and unless it goes to the next level. Is it right? Is it right?
Yes, sir.
So the tree with root alone is the height is 0. That is a standard implementation, standard discussion. Even in the professor lecture, he talks about. Now, very easy and important question. Very frequently they are asking in the quiz. They will tell you that. What is the maximum and minimum nodes with height something like some particular value, maybe they say that 3. What is the maximum possible nodes are possible in the binary tree, what you can call binary tree? What is the minimum number of nodes possible in a binary tree with height of 3? So in this case, it's a standard formula. How to find that maximum nodes is very simple. That is 2 to the power of h plus 1 minus 1. So 2 to the power of h plus 1 is 2 to the power of 4. Is it right? 2 to the power of 4. So 2 to the power of 4 minus 1 is 2 to the power of 4 is 16. 16 minus 1 is 15. Am I right or wrong? Am I right or wrong? Hello? Hello?
Yes, sir.
This is the maximum nodes. How can you do it? Is very simple. So they said it is height is 3, no? So 0 is having at most 2 children. This level is having at most this, 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 this. This level is having at most this. Is it right? Is it right? Maximum is this much, no? This is 0th level, first level, second level, third level. So how many nodes are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is matched. Is it clear? Is it clear?
Yes.
Maximum possible nodes. The minimum is very simple, h plus 1. Minimum nodes is just h plus 1. If height is 3, so minimum possible is 4. So what exactly, For example, you are going left skewed tree. Left skewed. Left skewed. See, it is 0th level, first level, second level, third level. How many vertices are there? This is 1, 2, 3, 4. So which is equal to 4. This is the minimum. Left skewered means always we are going to the left side. Right skewered means right. So that this is the standard questions we'll ask you. Very simple formula. So what is the height they are given? 2 to the power of h plus 1 minus 1. You get it the maximum possible nodes in a binary tree. So minimum possible nodes is just h plus 1. So that is a left skewed one or right skewed one. Up to this, is it clear? Is it clear?
Yes, sir.
These all the theoretical concepts only. We are not entered into any kind of algorithm. Only just we are understanding the tree basics. Yeah, still basics are there. Up to this, the basics are clear. Okay, fine. Yeah, so still some more basics. Now, how to implement these trees? Because tree we are represented as a graphical format. Just it is drawing, just simply vertices and edges we are drawing. We want to convert into digital format, digital implementation. Just like the graphs we are implementing using adjacency list and adjacency matrix. Is there any way to implement the trees using digital elements? Yes. So simply we are using, if it is binary tree, so binary trees, we always implement using lists or arrays. Lists or arrays. Because some other language they call it arrays, but in the Python they call it as list. But make sure the binary tree the binary tree should be complete binary tree, then only possible complete binary tree. So let me tell you what is complete binary tree. So the complete binary tree is simple. Sorry, maybe I may not give the sufficient place, so I use this. So yeah, here it is, unused space is there. Yes. So here, so let's understand the complete binary tree. If it is complete binary tree, then only we can do that. Complete binary tree. We know already binary tree property. It has one or none or two at most children is possible. At most two children. So the complete binary tree is simple. The complete binary tree is filled level by level, and left to right, except except the last level, except the last level or last nodes, what you can call it, except that last nodes. So let you take that.
So
So
does
hmm,
so does it mean child?
yeah, last nodes means last leaves, last child. Yeah. So look at here. I'm taking one example, maybe something like 26, one particular a random tree I'm taking. So 2, 9, maybe 21, 3, maybe something like 41. So here you can see this. This is a root. Is it right? This is a root. Is it right? Hello. Yeah. So what is the level number this? Which level is there?
0.
Yes. So 0th level is filled. Is it filled? No. The 0th level, one node is filled. It's a maximum. We cannot fill more than one root. It's okay. So the next level we are going. Level number 1. So is it two elements are filled or not? Is it filled?
Yes, sir.
So that no problem. This level also filled. Now we are going the second level. In the second level, so actually you can fill more. It's a 4 elements, but we have filled only these 3. Is it okay? Yes, no problem, because except the last nodes you can do the filling, but filling strategy is level by level, left to right. First you need to finish the level 0, level 1, level 2. So this tree is called complete binary tree, or we can say that uh, near to complete. Am I right? Am I right or wrong?
Yes, sir. I get that.
For example, one more example I'm taking. So that 7, 36, 2, 9, 7, 4, and 6. What is this? Is it complete binary tree or not? All levels are filled.
Yes, sir.
All levels are filled. Filling is left to right, so that it is a CBT, complete binary tree. I'm going another one. Another tree I'm making. 0, 6, 7. I'm making 2. I'm making 36. Is it complete binary tree?
No, sir.
No, because see what exactly this level is filled. Fine. Level 0 is filled. No issue. Level 1 is filled. No issue. But whenever you come to that level 2, the filling must be left to right. So they filled this, no problem. But there is a hole. There is a hole. By leaving these 2 holes, they are trying to fill the fourth particular loop, so that it is incomplete. What you can call incomplete. The complete is possible. Filling must be left to right. We should not have that holes in between, that left to right. There is a particular hole here, there is a particular hole here, unfilled space. It's not possible. Then only we can say the complete binary tree. So the complete binary tree only can be represented with lists or arrays. If it is incomplete binary tree, we cannot. So complete binary tree means don't worry, even nearby complete also no problem. Both of them are same functionality. Complete, nearby complete. Nearby complete means maybe last nodes are not filled, but filling is left to right is going on. Each level by level they are filling, no issue. Then that is called as nearby complete. Is it clear what is complete binary tree? Is it clear?
Yes, sir.
Still we are in theory concept of the trees only. Now what is the advantage of this complete binary tree or nearby complete binary tree is, so the first one is finding root of any element. I'll tell you one example also. So right of any element, right of any node or any vertex. Similar way, left of any vertex, any vertex. Now let's consider a list I'm taking. Maybe I'm taking a list. Just I'm taking a list. The list is like this. Maybe I'm taking it as so earlier values only 26, 2, 9, 21, 3, 41. I want to make a complete binary tree this one. So it's very simple. 26, left is 2, right is 9. So 2's left is 21 and 2's right is the 3. 9's left is 41. Yeah, it's all covered. So let's you consider these are index positions 0, 1, 2, 3, 4, 5. So this is a CBT, complete binary tree, or nearby complete, no issue. Nearby complete doesn't create any kind of trouble for us. It doesn't create any error. Now, finding the root of any element is very simple. What I can do is uh, the list of I minus 1 divided by 2, I can get a parent. For example, who is the root of 41 I want to find out? What is the index position of the 41?
5.
5. So 5 minus 1, it's a 4 divided by 2. What is the one you are getting? It is sorry, it is getting 2. Is it right?
Yes, sir.
Hello. So what is the second index position you are having? 9. Did you get the root?
Yes, sir.
That's okay. So similar way, the left of any element you can easily find out. How to find the left of any element is very simple. That is 2 into index position I plus plus 1. You get the left. For example, who is the left of these two I want to find out. What is the index position of these two? 1. So 1, sorry, 2 into 1 plus 1. So 2 into 1 is 2, plus 1 is 3. So the left of this 2 is, so third index position, that is 21. Did you get it? So similar way, right also. So that is 2 into I plus 2. So this is works except for root. We don't try further because root is the ultimate one. Above root, we don't have anything. We can try root below. But these things works for all cases. Like left of any element, right of any element you want to find out it. But this particular unit of, so how much complexity of this particular finding of index position is, just it is finding element of the array using index position. This computation is just unit of time, no? Is it right? Unit of time or not? A divide operation or multiplication. Is it right? Hello.
Yes, sir.
So that this is the advantage of using CBT. Why do you prefer the CBT is this? For example, I want to build a binary tree, but it's not a CBT. Then you supposed to implement that using linked list. Already you know linked list data structure. Do you know linked list data structure? No. A node is having a data and it is having a left reference is there, right reference is there. Am I right or wrong? So you
Yes, sir.
use it that one. Don't use that list or arrays. List
So
or
double.
arrays are compatible if and only if it's a complete binary. If it is a not a complete binary tree, you're supposed to depend on linked list. Yeah,
So is it a single linked list or double linked list, sir?
double linked list. But it is a double linked list. We don't use it, previous and next. Instead of previous and next, we use left reference and right reference. That's it.
Okay, sir.
Simple. So this is a complete overview of it. Just we walk through it, but actually, I think They did not tell you that much about it. They directly talked about max heap and min heap, but I don't want to directly jump to the max heap and min heap. First, we try to understand what is the binary tree. So binary tree data structure, which each node contains at most two children, so which it is referred as left child and right child. But remember, when you are trying to build heaps, make sure it is filled level by level, left to right. As I said, it is a complete binary tree. They are calling it as heap because heap is a one data structure. They try to implement it. Of course, max heap is there, min heap is there. There are some certain algorithms are there. We use it max heap algorithms and min heap algorithms. But remember, we represent heaps using arrays. As I said, 0th index is the root, first and second is the left descendant, right descendant, and keep going. So up to the 10 elements you are accommodating from 0 to 9. It is nearby complete or complete. Both of them are same because we are filling level by level, except the last level, not issue. The last level you are filling only the certain number of children. Remaining things might be there, but poles are not entered. For example, you cannot have, instead of this particular one here, I cannot have h9 here. Then it is not a complete binary tree because this whole creates a problem. Is it right? Is it right? So that you need to take care about it. So holes should not be there. And as I said, it is a list of elements. How to get that left child is simple. The 2 into index position plus 1. How to get the right child is 2 into index position plus 2. So left index, right index. And parent of it, if you want to find out, it is ith index minus 1 divided by 2. But thing is, you cannot do it for root. Root is the ultimate one. Any particular child you want to find out the root of the child, you can find out. But root itself, you don't have any root. Except for this I is greater than 0, you can do it this parent finding for other particular children. So this is how really, the tree basics. So actually you implement max heap and min heap. We'll discuss in the next session because I don't want to dump all of the things now itself because some part of 5th week we have worked, some part of 6th week we worked it. So because upcoming we have a quiz examination and live coding session also coming Friday, it will not be there. We'll discuss mock questions and as well as any previous year questions you have in TA session you can discuss, as well as coming Friday session you can discuss. So please open for any clarifications about the week 6. Please let me know because I don't want to take much time. Completely, I don't want to spend today itself on the week 6 because we have still time because we are in very advanced. Go ahead, we are ahead of time. That's the thing we are pausing. Yeah, recording we are doing session, but live streaming is not happening. So hope you got everybody last recorded session also. Did you get it? The sheet is available on the in your dashboard. Is it there? Your eyes accessible? Hello. Hello.
Actually, sir, the previous day recording we can access from the calendar actually.
Yes,
I
yes.
I,
So
I
this
didn't
one,
take the sheet actually, but I saw in the calendar it's there.
yes, yes. So today also recording is there. That recording again we'll add it to the calendar because there is an issue in the YouTube streaming. So once that is sorted out, and we'll post it in the PDSA channel also. But before it, you can access it by tomorrow. This one through calendar, no issue. Today's session also. Yeah.
Okay, sir.
So I think it's pretty much that because I don't want to spend your more time on this today because we have coming quizzes there. So please ready for the Friday session. I request you that don't miss the Friday session because almost we have 16 or 15 questions are there in the mock. If you possibly follow the mock quiz questions, you can easily attempt that quiz one examination on Sunday. So hope it's clear. Shall we close the session?
Yes, sir.
Yeah. So thank you. Have a nice day.
Thank you, sir.
Yeah, we'll meet on Friday, but Friday session is very important.